Hey, I'm Jason. Welcome to the Half Garage Workshop. Today, we're getting blue balls in the shop. Hey, so the last time we were in the workshop, we made this radius turning tool so that we can cut out spheres or other curved shapes on the lathe. On camera, we made a new ball that's a handle for the tailstock of the lathe, and then I also made a second one that is the handle of the tool that we actually made. And I think they turned out nice. The aluminum spheres look really good. But if you look around the shop, I've got sort of a color theme going on. Other than machinery gray, my second color in the shop turns out to be blue. My welder is made by Miller. I'm on team blue when it comes to welding. So that's blue. If you look at the milling machine, the cart which I built for the milling machine is blue. The frame of the machine is actually, and the vise are blue as well. I've got a blue vise over on the workbench, and there's some other stuff all around the shop you'll see over time that they're sort of carrying through on that blue theme. So I think it would look pretty good if the balls that we made were blue as well. Now we could paint them, that would be okay, but paint kind of rubs off over time, and it would be a really boring video just watching some paint dry. So instead, what we're going to do is anodize these aluminum balls and then dye them blue. So stick around and I'll show you how it's done. So if you've worked with aluminum in the shop, one of the things that you might have noticed is that when it's freshly cut or polished, it has it can have a very shiny mirror-like chrome appearance. But after a few hours or a few days, it'll become a little bit grayer and not quite as bright. What's happening is that oxygen in the air is combining with the aluminum and forming a very thin layer of aluminum oxide. Now this is actually the same thing that happens to iron when it rusts. We have the oxygen combining with the iron and forming iron oxide. The difference between aluminum and iron, though, is that iron oxide is much softer than the underlying material, so it can flake off, more oxygen can come in, and you get rust that builds up, and eventually the part will be turned to dust. With aluminum, though, aluminum oxide is very hard. It's a number 9 on the Mohs hardness scale, with diamond being a 10. And in fact, you can get sandpapers that are made with aluminum oxide as an abrasive. The layer of aluminum oxide that forms on our parts is very tightly bound to the underlying aluminum, and it protects it so that no further oxidation can happen. Now in anodizing, what we do is we use electricity to make that thin layer of aluminum oxide thicker. We can have it almost 1/1000th of an inch thick, which is a lot thicker than just a few molecules thick that it would naturally form. The other advantage that we get is that the layer that we cause to be created has sort of a honeycomb appearance with pores that we can then fill with a dye to give it whatever color we want. Most electronics that have aluminum enclosures that you have in your home have probably been anodized. So if you have an iPod or a phone or something like that that has an aluminum case that can get in different colors, it's been anodized and dyed. So that's what we're going to be doing today. Now the surface finish that you get before and after anodizing is going to be the same. So if you have a shiny chrome-like finish, you're going to get a shiny colored dyed surface. If you have a matte or a rough surface, it's going to be matte or rough when you're done. Our parts that we made, the balls look pretty good, but there's still some scuffs and some tool marks. So let's take these over to the lathe and we'll use our Scotch-Brite to give us a nice brushed metal appearance on the parts before we carry on with the rest of the anodizing process. Okay, that looks pretty good. So one of the most important factors that will determine whether we succeed or fail in our anodization is cleanliness. Any greases or oils that are on the part, whether it's from cutting oils from the lathe or just from my fingers, will interfere with forming that layer of aluminum oxide that we want and will cause us to get a bad finish in the end. One way we can tell whether the part is clean enough is by doing something called a water break test. So we can take some just distilled water in a spray bottle, spray it on the part, and if you see now it's beating up on the surface. That's because there's oils either from my hand or from the lathe that are on the part. So what we need to do is very thoroughly clean this so that instead of beating up, the water breaks off and slides off almost in a sheet. I'm going to take this into the house, use some commercial degreaser, and very thoroughly clean our parts, and I'll bring it back and show you how it goes. So we got our parts clean and degreased. We're just going to do the water break test again and make sure that the water is now not beating up on the parts anymore. It just rolls and sheets off them. We'll check both. And as you can see, we got all the greases and oils off the part. So We should be good to go. Okay, now that we've got our balls nice and squeaky clean, the next step is going to be to attach them to this aluminum bar that we're going to be using to hang the balls from when we're submerging them in the tank to do the rest of the process. So what we're going to be using is some aluminum wire. You could also use titanium wire if you have it. The titanium wire would have the advantage that it could be reused. The aluminum wire is going to get anodized itself, so it's sort of a one-time use thing, but I don't have titanium wire. I do have aluminum, so this is what we're going to be using. I cut off a few inches of the wire so they'll hang at the height that I want, and then I took the end and just hammered it and pounded it down flat so that I can get a nice tight fit in the holes that we have in our balls. So let's get those shoved up in there so we got a nice firm connection. Yeah, somehow it always ends up so that the one on the right hangs a little bit lower. Do you guys have that happen to you? Alright, from here on out we're going to be dealing with some semi-nasty chemicals, so I'm going to make sure we're taking proper safety precautions in the shop. I'm wearing my shop apron, I have gloves on, and I'm wearing a full face shield, so I protect my eyes and face from any splashing. The next step that we're going to do is etching the parts before we anodize them. We're doing this to rough up the surface a little bit and also to clean off any final impurities. Now this step is kind of optional. If you want a super polished finish, you just have to make sure it's extra clean. But since we're going for kind of a brush metal appearance, a little bit of etching on the surface will be fine. To do that, we're using a solution of sodium hydroxide in water. Sodium hydroxide, you can buy it as lye, as a drain opener. I've had maybe 200 grams or so of sodium hydroxide dissolved in about 2 liters of water. So we're going to put our face shield down. All right, then we're just going to dunk the parts for maybe 15 seconds or so. You can see bubbles will start forming, where the sodium hydroxide starts etching away at the surface of the aluminum. As soon as you put it in there, we're going to leave it maybe 10, 15 seconds or so. Let it make sure it eats off any bad stuff that's on there and get a nice little etch going. As soon as it's done, we're just going to rinse it off in some distilled water. Okay, that should be good. Let's just spray it down a bit with some of our distilled H2O. Rinse that lye off of there. And we'll give it a good dunk in our fresh distilled water. Alright, now that we got our parts cleaned and etched, we're ready to anodize them. So to do the anodization, we need 2 things. We need an electrolyte solution that we can submerge the parts in and pass a current through them, and we need a power supply. For the electrolyte, we're going to be using a solution of sulfuric acid and water that we'll be putting together here in just a minute. For our power supply, well, we could use like a car battery charger, which would work. It's a constant voltage power supply. It would allow us to do the anodization, but it wouldn't give us much control over the process. The problem is that because it's constant voltage, it's always going to put out 14 volts to charge your car battery. The amount of current is going to vary over time, and it's the current that lets us know how thick of a layer of anodization we're building up. And with that current constantly changing, it would be really hard to know if we're done, if we've gotten enough time in, and we'd have to kind of guess at it. Instead, what we're going to use is a lab bench power supply. I have a surplus Hewlett-Packard power supply that we can set up to be a constant current source. And that current source will let us have much more control over the anodization process. So to use that, though, we got to do a little bit of math. Now, it's only algebra. It's no trig involved this time. And hopefully now I won't have to call in my 17-year-old daughter like we did in the last video to fix my math. I'll put it up on the screen here so you can see what we're doing. We're going to be using something called the rule of 720. It's a rule of thumb for anodization that tells us the relationship between the current density, how much amps we're pushing into the part, the time that we let the cell run for, and the thickness of the anodization that we get. So the rule of 720 says that the current density in amps per square foot times the time in minutes divided by the thickness in thousandths of an inch, or mils, or thous, same thing, is equal to 720. Now there's also a metric version of the rule. I believe it's called the rule of 312, which gives the same relationship, but instead it's currents in amps per square decimeters, and thickness is in microns instead of thou. So you can look that up and do the same calculations and it'll also work there, but we're going to be using English measurements. So we've decided we want to have about a 1 thou thickness for our part, for our anodization. That should give us a good result as far as the dyeing goes. For the current density, we got to decide what current density to use. Now, commercial anodizers can use much higher current densities, up to say 30 amps per square foot. We're going to be doing a much lower range. Lower densities will cause the pores to be a bit bigger and make our dyeing go better. It doesn't give us quite as hard of a finish, but we're more interested in the dyeing. So we're going to use about 4.5 amps per square foot. If we rearrange the formula and we plug in the 1 thou for our thickness and the 4.5 amps per square foot, do some math, that will give us 160 minutes is what it comes out to. So hopefully that's right and we're all following along. So now that we know the time, the next thing we need to know is the amperage. What do we need to set our power supply to? To do that, we need to figure out the current density, and that's just amps per square foot. So to figure out the square footage, we need to figure out the surface area of our spheres. Now, each of the spheres is 1 inch, or about 25 millimeters. The formula for the surface area of a sphere is the surface area is equal to 4 times pi times the radius squared. So our radius is 0.5, or half of an inch, and we multiply that by 4 by pi, and we get 3.14 square inches per sphere. We've got 2 spheres, so we'll multiply that by 2. We have 6.28 square inches. Now we need to know our area in square feet instead of square inches, and here's the point where the metric people are going to laugh and make fun of me, but 1 square foot is equal to 144 square inches, so we need to divide that by 144 to give us 0.04 square feet of surface area. So now that we know our surface area, we can figure out the current that we need just by multiplying it by the surface area by the current density, well, 4.5. We do that math and we get 0.196 amps, or about 200 milliamps. So our plan is that we're going to run our anodization at 200 milliamps for 160 minutes. It's 2 hours and 40 minutes, and we should get a good 1 mil thick layer of anodization on the parts. So let's set up our anodization tank and get started. So to make our anodizing tank, we're going to start off with a clean bucket to which we've added 1 liter and about 1/3 more of distilled water. Our final electrolyte solution, we want to have a 2-to-1 ratio of water to acid. So we want 2 liters of solution, so 1 and 1/3 of distilled water, and then 2/3 of a liter of our battery acid will give us the right ratio. The cathode, the negative electrode of our cell, is going to be lead. We could use aluminum, but the aluminum would get dissolved over time, and whereas lead won't. It's pretty much inert. So we'll be using this piece of sheet lead as our cathode. So we'll add that to the tank. Push that all the way down, pull it over there in the back, and then we'll connect our negative electrode when the time comes to that. So now we would need to add our battery acid to the tank, or the sulfuric acid. So I'm going to put my face shield down, open up the container, and then top off our tank up to 2 liters with the battery acid. Okay, now that we have our acid added to the tank, the final thing we need to do before we can add our parts is we need a way to agitate the solution, keep it moving around so that bubbles don't form on the part and cause us to have some uneven anodization. To do that, we're going to be using a little aquarium air pump and an air stone, which we'll add in. So we'll put that in the bottom of the tank, plug it in, and the bubbles will keep the solution moving around. All right, now we're ready to add the parts and hook up the power. So we'll take our cleaned and etched balls that are racked up, put them down in the tank. We want to make sure that they're not touching anything, that they're not touching the anodes or the each other or the sides of the tank. All right, so now we can connect our electrodes to the part. We're going to connect the positive electrode from the power supply to the anode, to our part, and the negative supply is going to be connected to our lead cathode. So this is the power supply we're going to be using. It's a Hewlett-Packard DC Lab power supply that I picked up from a surplus store for about $100 a few years back. And it really works great for this kind of job or any other kind of project where I need a constant current or constant voltage source. So for this, we went it in constant current mode. So we're going to set the current to the 200 milliamps we said we would need. Okay, I temporarily turned off the air supply for the agitation so we can see what's going on in the tank. I'm going to hit the output enable button on the power supply and we should see the process start. Let's go. All right, if you look closely, we should start seeing a little stream of bubbles appear from the parts where we're anodizing them. And yep, there you can see it right there. That tells us that current is flowing into the anode, into the part, and then through the electrolyte to the cathode and back out to the power supply. So our anodization should be working just fine. So I'm going to start a timer, let this run for 2 hours and 40 minutes, and we'll come back and check and see how we did. Okay, time's up. It's been 2 hours and 40 minutes, or 160 minutes since we started. And as you can see, the voltage that our power supply has been putting out has increased as the resistance has gone up all the part as the anodization has happened. So let's shut down the power supply and turn off our air stone and pull the parts out and take a look. Okay, you've got a dull gray appearance from the layer of aluminum oxide that we formed on it. What we're going to do is take our distilled water, spray them off, get them cleaned off so we get all the acid off. It's very important to get all the acid off or the die is not going to take. And then we'll give them a rinse. Okay, while those are rinsing, I'm going to clean up here and then we'll get set up to dye them and see how it turned out. Alright, now that our anodizing is done, we get to try to dye the parts and see how they turn out. Now, the dye that we're using is from Caswell Plating, which sells a whole lot of anodizing and plating supplies. You can buy whole kits where you're going to use a blue 4A dye. Now, this dye needs to be diluted, and it says that this 4-ounce container would add it to 2 gallons of distilled water. So we're using 2 quarts of water, so we'll need about 1 ounce of dye, which is about 30 milliliters. So let's add that in. The dye also needs to be at 140 degrees. So to keep it at the right temperature, we're going to use my sous vide cooker. Now the sous vide, in addition to making a great steak, is also a very accurate water bath. So it can hold the water temperature right at 140. So we'll keep our dye right where we need it to be. So let's add this in. And we'll give it a quick stir to mix everything up. All right, the dye is ready. Let's take the parts out of our water bath where they've been rinsing. Dunk into the dye and see how we did. Okay, we need to let those sit for about 15 minutes or so, and then we'll come back and check. So the balls have been in the dye for about 15-20 minutes, so it's time to take them out and see how we did. Oh. Okay, it looks like it worked on one and not on the other. And if we take a little bit closer look, I think that what happened was the connection to the ball that didn't get anodized wasn't quite solid. You can see it's wobbling around there a bit on the wire. So what I'm going to do, I'm going to take the this apart, remove the ball that didn't work, and re-anodize it off camera. But in the meantime, we're going to just carry on and continue with the one ball that did get anodized and seal the dye into the part, and let's just see how that works. Well, we're down to only one ball, and I'm going to avoid making the obvious jokes and carry on. The last step that we need to do is to close up those pores that we created in anodizing and seal the dye into the part. To do that, we've increased the temperature on the sous vide up to max, so we're just right at the boiling point. We have a fresh container of water, distilled water in the bucket, and what we're going to add to it is some nickel acetate. Now this is actually the nickel plating solution that I used in the first half garage workshop video to nickel plate the maker knife, but we're going to use it now to aid in speeding up the sealing process. So we'll add the nickel acetate to our distilled water. And then we're going to take our anodized and dyed ball and submerge it in the water and leave it to soak for about 10 or 15 minutes to close up those pores and seal the color in our part. Okay, we've had about 15 minutes in our nickel acetate sealing bath, bubbling away there. So let's pull it out and see how we did. All right, looks pretty good. I'm gonna give it a final rinse, and then I'll redo the other one off camera and bring you back when it's done to wrap things up. We're back at the workbench, and while we were off camera, I did go back and re-anodize the second ball. I think if we take a close look here, we got a really nice result. You know, nice even blue deep dye, similar to the first one. In fact, maybe it's a little bit deeper color. I went back at on the video and looked and saw what happened. I'm pretty sure what occurred was the way we had the parts attached and racked up in the tank. Originally, we were using some aluminum wire, which I had hammered flat, and then had that shoved down, wedged in the bottom, trying to get this to hold onto the threads. And looking back, I think it wasn't a good enough connection. We just didn't have enough surface area of the wire making contact to get us a good flow of current into the part while it was anodizing. So while it worked on this one ball, which actually has a smaller size thread, on the ball that goes on the tail post, which has a 1/4 20 thread, a larger thread, it just was not tight enough to get the job done. So what I did was I took a piece of aluminum bar stock and turned it down to a 1/4 inch and threaded both ends so it matches the thread of the ball. We just had that screwed on there nice and tight, so it made really good contact. And you can see we got good anodization of the rod too. On the wire for the ball, you can see we got it anodizing up here, but once we got down into the part, we lost that contact and we didn't get it anodized anymore. So we had the ball threaded on there, and then I also ran a tap through my anode bar that we could get a good solid contact to get the job done. So I think the one lesson learned here from the process is that maintaining really good electrical and mechanical contact when you rack the parts up to anodize them is key to getting a good result in the end. So I'm really happy with the way that turned out. Well, as always, I want to thank you for hanging out here and spending a little time in the Half Garage Workshop. If you made it this far and enjoyed what you saw, please take a second and hit that thumbs up and let us know you liked what we're doing here. If you have any questions or comments, please leave them down below. I really enjoy seeing the feedback and reading what everyone has to say about the projects we're doing. And if you want to see more content, make sure to subscribe and hit that notification bell so you'll find out when we post new stuff from the workshop. Until next time, have fun, stay safe, and I'll see you back soon in my Half the Garage.